the host side is then plugged into a bridge, right? So now we take that same scenario and multiply it across 10, 100, 1,000 containers, and now we've got all these containers that are able to communicate across this virtual bridge on this host. And that's just one example. I mean, there's namespaces for BID, networking, there's storage, C groups, and again, you can go and go to Wikipedia. I would urge you to spend some time getting into the details of these different kernel facilities so you really understand what's going on. And these are just the container runtimes or container engines, kind of interchangeable term there. But Docker is the 800-pound gorilla in this list, and Docker is even morphing way beyond just a container runtime. Rocket is backed by CoreOS and is part of the Open Container Initiative. But again, these are just your common runtimes. And if we look at Docker in a little more detail, just a quick background, and I mentioned it a few minutes ago, but they really brought containers to market, even though containers, the technology behind containers were there, LXC was there for quite some time. But Docker made it easy and exposed the capabilities through a well-documented open API. And beyond just the runtime itself, there's functionality for building container images, a registry so that you can store these images and pull and push to the registry, a way to manage those container images. And then way beyond that, even since I put this thing together, there's the Docker toolbox, so all the tools that you want as a developer to make it easy to develop your applications on Docker. There's the unified control plane that came out a few months ago, and now there's Docker Data Center, Docker CAS. So Docker is just morphing from this container engine to a full-on application platform. And I would even say beyond that. So Docker, when Docker says, let me go ahead and instantiate this container, it can go ahead and call LXC, right? So go ahead and actually do all that plumbing that I showed you in the previous slide, create this namespace for networking, create this PID namespace for process isolation. Well, one of the things, I think this in fact Docker 1.3, and if anyone knows correctly if I'm on there, but actually Docker came up with its own execution environment, written it up, and became the default, so that they don't have to rely on LXC and limitations and so forth. And I want to say there's one other execution environment that it supports, but I forget what it is. And then the Docker images, it's not just one big blob, right? I think of Docker images more like when I think about Git, right? If you think about how you can layer your commits on top of each other, think of it the same way from a Docker standpoint. And even some kind of Git functionality of tagging, pulling and pushing, but instead of source code, it's actually file layers or file images, right? So as you layer your image, you create an image. So a good example is what Cola, the project Cola does. There's multiple layers to the final Cola image. So if you go to Docker Hub and you look up Cola Glue, which is basically a repository for all of the Cola images, you'll see there's a Cola image for Nova Compute. Well, Nova Compute, if you look at the Docker files layered on top of like a CentOS image, and then that's layered on top of another base image. And so it's a way to kind of layer those images. So what it does is it provides you some benefits in the sense that if you want to make a change to one layer, you don't have to go ahead and kind of rebuild the entire
So you have these Docker containers you plop on there, sort of like sophisticated system on a chip type things. And then there's some type of interprocess communication. So really, is that only through sockets, or is there still like memory-based interprocess communication?
So yeah, when you look at this, kind of a high-level view of the architecture, right? So you've got your Docker daemon, and then you've got your Docker client. So when you do a Docker run, right, it's basically a client communicating with a daemon. Typically, you see the client and the daemon sitting on the same host and communicating over a Unix socket. But you can also expose the Docker daemon over TCP. Right? And so if you do that, you want to make sure it's secured, and this means using SSL to secure that communication.
Do you mean between containers or to the Docker? Okay.
Containers communicate like they would over a standard communication mechanism.
Think that they're separate hosts.
Yeah, they're separate machines.
They seem to be separate machines.
Okay,
So think of them like separate machines, but just much smaller, more efficient, more portable.
You don't really level saying I've got pipes and shared memory.
Yeah, because when I gave you the example of like network namespaces, again, think of that when I stand up at a container from a networking standpoint, I create a network namespace. I create 2 virtual network cards and a cable between. So the only way for this process in this container to communicate outside of the container is TCP. And that's typically, right, best practices is you've got a single process that within your container. Right? And that's one of the big differences between like LXC and and I think there's still a lot of battle back and forth on, okay, well, if it is a single process, maybe I like to go down.
I say a single service. I mean, it could be multiple processes, but it's a single service. That's what you're exposing in a container.
Yeah, because there is that argument between an init system running within your container or not. I prefer the init system, a stripped down container-focused init system, but most of what you see out in the world is a single process.
There's one other way. So containers can mount file systems back on the host. So our containers log to our log. All the containers are sharing that. This could be a machine.
But I think that's a little bit different than what he was.
No,
Yeah,
it is, but it's not just TCP.
It's not complete isolation.
They can talk to the file system if you tell it to
But
bind.
the thing is, if you go back, right, in that example, right, you're just from a storage standpoint, it's like, you're just exposing resources on your host and in the host non-namespace to that namespace of the container, right? And to your point is, well, you can have multiple containers access that same resource that's sitting on the host, right? Forward one slide into that one. How do you reconcile that with a single processor? Well, this is an image and not a running container, right? So you have an image that you go ahead whenever you do a Docker run, you say, what image am I running this container from, right? And so within that run, right, look at the Docker documentation. It's, well, not only do you specify an image, but then you have to specify a long-lived process to keep that running, or a short-lived process, because I was just working with a Python container. I'm literally putting a Python interpreter inside a container, and every time I want to issue Python X, like Python Y, it literally calls the container that runs Python because the operating system can support it.
Is this layer used versus Docker has it, or just kernel stuff that is exposing that other data?
This is Docker specific, right? The layered imaging, and there's a few good white papers that I've read. If you just kind of Google Docker images and layering Docker images, I would spend some time really understanding it, because that's the other part that is really attractive with Docker is they got the image stuff. They did that really well, right? And so
And it's a different
portability to move your container around, right? So it's like 2 major concepts. You got your image and the container. It could have just been a single tarball like what LXC does, right? Because and same with Rocket. So there's an argument both ways. Like, do you do layer? Because when I worked with Cola for a while, it was a pain in the butt sometimes because if I made a change to this base image, these 20, 30, 40 other different images that are based on this base image now had to get updated because they were, I had to patch something in this base image. Okay, and if I was running one of my other containers, again, let's say it's the Nova Compute container, you look at the Docker file, it says, one of the things is what's the base image, and I would say that it's the CentOS base image. And unless I went ahead and updated it, there'd be broken functionality. And so I think there's an argument for both ways, and I would say even spend that time, look at the Rocket documentation on why CoreOS prefers that using a single hardware.
Is AUFS required for the layering stuff?
Yes.
Okay. So that's more of a functionality exposed by AUFS.
Right, right.
Actual Docker.
Yeah. So I think we covered that. Again, just a couple screenshots of just what you can see here. So, each of these layers that that make up an image, I can push, I can pull. When I go ahead and pull down an image, or when I run a container and I say, from image foo, and that container is running, and I could go in that container and I could say, oh, great, this is a running container based on an image foo. I want to go ahead and add a package to it. We'll call it package bomb. Well, I didn't change the image. I added a new layer on top of that image. And now I can go ahead and say, let me go ahead and save that to a different version of that image, right? So now it's no longer foo latest, it's foo with the tag modified or something like that. So again, it's a little bit more like this. Here's the versioning. Let's see, images, I tag, and I can see that I now have a new tag. And so I said, hey, let's do a Docker run based on this image, and here's the executable. Please do the and I can list running containers. You see the ID, the image that it's based off, the command that it's used to keep it running, its status, and so forth. Like I said, you go into that running container, just like I showed you in the previous slide, make changes to it, and you'll see all the different changes. And then when I go ahead and save that container, it becomes a whole different layer to the previous image. So, talked about kind of the tech behind containers. We dove into Docker a little bit more to understand basically the de facto standard for containers. And now we get into, well, great, I have multiple hosts, maybe hundreds or thousands of hosts that I want running containers. How do these containers, how do I manage containers and that container infrastructure? How do I make containers communicate with one another across the different hosts and so forth? And you may hear it as container clustering engines, container management systems, container orchestration engines, whatever the term is. The field is essentially Kubernetes and Docker Swarm. And both of them have their advantages. I would say that in my experience, Kubernetes is leading the market, partially because they were first to market. But it's still very early, so we'll see what happens. So let's get into some of the Kubernetes basics. One of the things is Kubernetes can run anywhere, right? So you can run Kubernetes in virtual machines on physical hardware. You can run it in OpenStack and AWS and GCP. And there's a concept of a node. We think of the node as a worker within Kubernetes. Right? This is the the service or collection of services that's actually doing all the work, running containers and in Kubernetes terms, it's pods. Now the reason for that is there's a pod abstraction, and the pod within Kubernetes could have one or more containers that share the same network namespace. And the reason for that is that there may be certain helper programs, something like that does log rotation for your main program that you just want to bring together. So when you bring one or more multiple containers into a pod, that becomes a single unit of management and measuring within Kubernetes. What I mean by that is I go ahead and say, okay, stand up pod foo, and pod foo contains multiple containers. Kubernetes scheduler will schedule all those containers within the pod onto a single host, right? Because you basically designed the pod that those containers are meant to be with one another.
So it's kind of a resource manager, like what goes on what hardware.
Yeah, so the services that make up Kubernetes, there is a API, there's a scheduler, there's a controller manager, there's something called a kubelet, there's a kube proxy, and I think those are the major services. So it's a RESTful API. The scheduler does exactly that. So when you go ahead and say, hey, kube API, go ahead and stand up this pod, after it validates the request, and hands it off to the scheduler, and the scheduler says, okay, based on maybe this policy or so forth, let's go ahead and schedule to node 1, node 2, node 3. So, and it's not even so much network adjacent. It's when you start thinking about microservices and you say, okay, I've got this primary service, but there's ancillary services that I basically manage together, right? And it gives you a little more flexibility because, for example, like with Cola, I mean, it was really painful to containerize some of the OpenStack services, and we kind of hacked around it a little bit to get some services to run in a single container. But in hindsight, the better thing to do is the pod construct where we go ahead and say, okay, there's still individual containers based on certain images that I manage. So if I go ahead and say, well, this helper program, the log rotator, I need to go ahead and patch the code there. It's still managed, but it's like you're meant to run with another service.
So I understand namespace is that all those containers and then they're the same zero, right?
Yeah, so they're communicating with each other like local hosts. There's a master node that, think of this within OpenStack terms as kind of like a controller node, right? So it's running your API, your scheduler, your controller manager, and the controller manager service is basically a layer on top of the API service. And it's querying the API, use a controller manager to go ahead and say, okay, instead of deploying a pod, I want to deploy a replication controller. And a replication controller essentially makes sure that X number of instances of your pod or pods are replicated. And so if you say, okay, I've got red pod, and I actually want multiple instances of this red pod for high availability, then you actually create a replication controller. And if I want 3 instances of the web pod, it's going to make sure that always 3 are running. If 2 are running, it's going to go ahead and normalize and bring the 3rd pod up and running. If for some reason, if there's more, it's going to start just running pod obviously like a 5-year. etcd, it's not, it's not specific to Kubernetes. It's a shared key value store for sharing configuration information, for discovery of services, and for basically a data store backend for Kubernetes. And etcd is developed by CoreOS. Uses a raft consensus algorithm to ensure all nodes that make up the etcd cluster have consensus. And simple curlable interface. It also has a client as well. And I just put this up here because if you're going to at all get into Kubernetes, you're going to learn about etcd as well. So I kind of gave you this example. This is what it looks like. You basically have a YAML that describes your pod, right? You give it an ID, you tell it which image that you want the pod to be based on, what port that you want to expose on the container. And here you actually, again, you see that we've got multiple containers. We've got the web container, we've got the log container, all within one pod. Each of them exposing their own TCP ports for communication.
So another way to think about this is from outside, it looks like that's a single server that's got 80, 80, and 5001 running.
Yes. You can, and so something that I've been interested in is kind of a variation of that. So if you look at Mac VLAN, take a look at Mac VLAN. I don't have a whole lot of experience in it, but I have dove down into IP VLAN. And one of the projects for computer networking that we're working on just recently support, added support for BGP, and I'm trying to get them to also add support for IP VLAN. But basically, it's, I talked about kind of two NICs connected by a virtual cable. Well, one of the NICs, instead of presenting that to the host OS, it becomes like a virtualization of the host NIC, and so you don't even communicate across a bridge. Mac VLAN is kind of the same way. It's at layer 2, so connecting that container through the host at layer 2 out of the physical host onto your network. But both Mac VLAN and IP VLAN are supported in the Linux kernel, which is really nice. But one of the things I like about IP VLAN is just that it really simplifies the networking, because when you start talking to you got a physical host, and now you got a virtual bridge in there with these virtual interfaces on one end and virtual interfaces in containers, and you multiply that across hundreds of thousands. The complexity grows, as opposed to saying, just have these containers connect down into networking. So I'm interested in kind of combining IP VLAN with BGP so that we could really have high scalability and simple networking. Where if you take a look at Calico, they're doing some good things now. I don't believe they support IP VLAN, but they do have a BGP side, and that's basically saying, okay, each of your hosts running containers communicate over BGP at layer 3. So basically, the hosts connect to the switch, and it's like a /30 between the host and the switch, and everything's communicating via BGP. Because up until then, what's become popular, even outside of containers, is overlays, and I just personally believe overlays are difficult to troubleshoot. They have scalability limitations, high complexity, blah, blah, blah. And so I think it's a shift towards more than But when I go ahead and create this pod YAML, I then go ahead and send that request to the Kubernetes API. And the Kubernetes API goes ahead and realizes that and says, okay, this is the desired state from Damien. And what's the current state? Well, there's no pods running in the main web server. Let me go ahead and try to schedule it. Let's hand it over to the scheduler. The scheduler saying, you got no nodes, and if there's no nodes here, it'd say we can't do that, right? But we do have nodes, and this kubelet is an agent running on these nodes, these physical servers, running the kubelet, and the kubelet is basically registered with the Kubi API saying, hey, Kubi API, I'm here, and ready to do work if.
So underneath, is this still using Docker?
Yes. Now, one of the things is, and I need to look where Kubernetes is at, but I'm highly confident they have good support for Rocket as well. So if you wanted to say, no, I want to use a different container runtime, I'll use Rocket. You can go ahead and keep the Rocket images, and instead of specifying Docker Apache, point to where your Rocket image resides, and I'll show you some configuration again. Everything I've done is around Docker. But if you're interested in that, I would look and see where they're at. But I remember seeing something that they've got pretty good support for I'm not sure. Yeah, even you can specify that there's a way that C groups are exposed to Docker and Kubernetes, where you can go ahead and limit the amount of I/O and memory and so forth and CPU usage. And there's actually example manifests out there. There's a concept of labels and label selectors, and so if you can imagine, okay, great, now I've got this Kubernetes cluster of maybe 100 or thousands of machines. Developers are going wild and spinning up containers or pods all over the place. But how do I kind of manage them at scale? And that's where the labels construct comes in, so that I can create a label. It's called the label name, find that simple key value there, right? That gets associated to any of my Kubernetes objects. I could apply a label to a service, a replication controller, a pod, so on and so forth. And on the flip side, there's label selectors, so that when I go ahead and create a Kubernetes service, and I want that service to work with a certain Kubernetes pod, there's a label and a label selector, right? So the pod would say, I'm label web, and the label selector would say label web or name front end. And that becomes kind of the glue between the service and the pod. I already talked a little bit about this, but replication controllers layer on top of the Kubernetes API, and it essentially becomes a template of your pod that the replication controller manages. And the big thing that it's doing is saying, okay, what's the number of replicas, and then querying the API to make sure that those number of replicas are running, and if they're not, bring it back to consistency. Here. So I think the last object that I touch on here is the service. So if you think of a service, right, pods come and go. You've got this Kubernetes cluster, and you've got hundreds of thousands of pods, and every time that pod is realized, it gets an IP address. And so if you've got an application that's made up of all these pods, and you want certain aspects of the application to have some consistency, you can start using a service, right? So I may have a backend that's a Redis backend that's made up of 10 pods. Right? Well, again, those pods can come and go. They have IPs that change. So I go ahead and say, well, my front end needs to communicate to the backend on a consistent IP address. We create a service called the Redis service, and I tell Kubernetes, realize that for me. I said, okay, great. Here's the IP address and the port that you want that Redis backend to have. And so as these pods come and go, my client or my front end application that communicates, instead of communicating directly with these pods and all of a sudden getting an error saying, this pod over here that maybe died or whatever it may be, whose IP address is no longer there. Well, I'm going to communicate through the service, and essentially what this is a load balancer that goes across all your nodes, and load balances whenever I want to go and hit this service. Let's say it's 10.10.10 on port 80. It's going to go ahead and translate that and proxy it using a proxy to the correct pod. And so again, in this example, it's a client hitting a front end service. So you've got an Apache front end, want to expose it, and my Apache pods, maybe 5, 10, 15, whatever it is, create a service, use the label and the label selector, right? So there's a selector making sure that I find the right pods, because all my Apache pods have one or more of these selectors that I'm going ahead and creating that partnership between the service and the pod.
How is the service one thing? Is that just a single thing?
It is. It's a single thing that basically all of these community proxies are aware, right? And they're basically using tables to go ahead and say, whenever this request comes in for 10.10.10.80, I know to translate that to the port and IP address that this pod is listening to. Same thing with this one over here.
Right. That service dies, like that master recognizes that.
Yeah, and if the service dies, you've got some big issues, because that service is being managed by your Kubernetes API, right? So when I talk to the Kubernetes API, I say list services, list pods, whatever it might be. And granted, it's storing that information, right, into the etcd cluster. So if your etcd cluster goes down, you've got bigger problems with just the service.
I just mean like the service and the load balancer.
Just think of it as like the Kubernetes object, and its role is to create this abstraction, right?
I'm just
And
thinking
so,
like from an HA perspective.
and so for HA, you would want to make sure that your etcd cluster is an actual cluster, and it's not just a single etcd node.
But this service, like I'm assuming what that actually is.
Well, it is naturally highly available, because this service is implemented by the Kubernetes proxy that runs on every single one of your nodes. So this node goes down, okay, a couple things are going to happen. The scheduler is going to know that node, whatever her name is no longer available, and it's not going to schedule it here. But if these pods here were actually part of a replication controller, then the replication controller that queries the Kubernetes API, right, the controller manager service, will go and say, hold on. This replication controller said there were replicas of 2. And now, because this is gone, let me go ahead and realize the second pod over here. And when doing that, because we use the label and the label selector, this pod is also associated to a service. So the Kubernetes proxy was informed by the kubelet to go ahead and create the necessary IP tables entries, so that whenever I connect to this service and it gets forwarded to here, it says, oh, you want to talk to this pod on this port. And
It's a single IP address, right? So that can only go one place. Like that. So you're saying like this whole thing exists on one host?
across all the different hosts.
Well,
Right, but how did the purple, I think.
What has
Every single
what
one
is
of
the
these.
service, what is the listener?
Every single one of these are listening to this IP address. Right?
Well, I understand they can all listen, but network-wise, like that IP might only get routed to one host, unless you did any caps or something external, right? You know, you see it every day now. But basically, what I'm asking is that purple box there, the service, like, what is that thing? Like, is it another container with a proxy? Or
So A is an object within Kubernetes that provides an abstraction layer so that you can expose your pods on a consistent IP address. Okay? And so whenever you want to expose a pod, you would want to use a service and you say, hey, I need a consistent IP address as well.
Right. Yeah, I guess what he's asking is, if you take a traditional HA proxy environment and I make a load balancing decision on reels behind the HA proxy, I'm not sending it to multiple reels at the same time, right? There is a selector of which one I'm going to, based on round robin, least connected, whatever. So what does the service front end do in relation to the two proxies? It's not, your arrows are showing that it can basically deal with multiple connections at the same time, but it doesn't, right?
Well,
It's actually
yeah,
using-
so what we're saying, I think, is you've got one thing with a layer 3 address.
It's not. This is just a conceptual object. So when I go and I
So
query,
what is providing that listener on multiple maps at 10, 10, 10, 10 that the client is actually connected
But they're all 10, 10, 10, 10.
so when you go and you go into the IP tables of this node and this node, you will see NAT translations saying any inbound for this IP address on this port translated to the pod IP and port, and vice versa. When this pod says, oh, I need to connect to the back end service, right? And somewhere in its application, it says, okay, resolve backend foo.bar. It resolves to the service IP of the backend. It says, okay, let me communicate to that and send it off.
How does the TCP send get to any specific box? Because you've got this purple service thing that looks a lot like a load balancer. But you're saying it's not.
Think of it like a virtual load balancer. So again, when you think of a service within Kubernetes, the first thing is that you think of it as an object within the system, a conceptual object. And its purpose, when you query the Kubernetes API, you say list services, it's going to go ahead and give you the list of services that you create. And an IP address
is
is more.
more pure network. I'm a client. I'm 208.11.11.
Right,
I
you're
want
this
to get
client
to
right
10,
here.
10, 10.
Yes.
How do I end up at the front end?
And this could be a client pod, right? So, the client pod, let's just try to walk through this, right? This client pod has some type of logic in there that says, I need to resolve front end. Oh, front end is this IP 10.10.10. So it goes ahead and sends TCP packets out to 10.10.10. Now, if this client pod is here, it goes across the network and it's translated across all these Kubernetes boxes to the associated IP and port of each of the different pods. Now, maybe there's also another layer, right? So this is within the Kubernetes system. Then there's a concept of externally exposing services, right? So in this example, it's okay, front-end pods need to talk to back-end pods. Oh, the front-end pods, we want to have a service there, so we've got a consistent IP and port to communicate on as pods come and go. But now, okay, great, my Kubernetes system of 100 or 1,000 nodes, I now want to expose my front-end service outside of Kubernetes, which makes sense, right? There's different ways of doing it, right? You can go ahead and use a node port, a cluster IP. There's a new object called an ingress within Kubernetes. The node port, when I create a service and I say I want the service to be exposed outside of Kubernetes, use a node port. It then instructs Kubeproxy to expose the service using a different high-ordered port number for that, right? So either Kubernetes will select a high-ordered port from a range, or you can go ahead and say, here's the port that I want to give it. And when, let's say this is E1 of this node, right? So now I can connect to it via the IP and port of this node.
Right, and I don't think that's the question.
No, I think I got it. I think you said something there. This is within Kubernetes. So, like, if you're a Kubernetes client talking to this in the same thing, there's a address translation. So, if you're the client, you're also on Kubebox that has Kubeproxy running on it. There's an address translation in there. So, for 10.10.10.10.80, that points it to one of the
Is this diagram showing the client inside the service?
This is inside the Kubernetes cluster.
So the client is inside the cluster.
Right. So outside you have to do service.
Okay.
It's inside.
But in the same token, right?
I was with you. I was interpreting that client to be, I'm on the internet coming in and service.
Yeah.
That would have saved us about
But the
10
same
minutes.
concept with the service, though, is like I said, you can expose it externally. I talked about the node port. The other thing is,
Yeah, though, because you're saying that there's a service thing, and you're showing that it maps to multiple proxy boxes, or physical box, or whatever, right? And somehow you have magic where 10.10.10.10, an Ethernet frame with a MAC address for 10.10.10.10 somehow gets to multiple physical boxes. Layer 2 switching doesn't work that way unless it's a multicast or broadcast.
but it's going to resolve, right? So when you're ARPing for it,
When I ARP for it, I get an answer.
right, and it's going to be from one of these nodes, and say, oh, do you want to talk to 10.10.10? Then let me give you my MAC address. Okay, so you can expose the service internally within the cluster, or you can expose it externally. When you expose it externally, there's a few additional steps there. One of the ways to do it is through a cluster IP, right? And what basically you do, for example, one of the cluster or external ways to expose a Kubernetes service is supported by OpenStack or AWS or GCP. Those are cloud load balancers. One of them that's supported is Azure, right? And so when you say service, I want you exposed outside of this Kubernetes cluster of whatever number of machines. It then makes an API call, authenticates to Keystone, and then says, hey, Neutron, spin me up this load balancer, create this virtual IP address, and associate the physical addresses of the nodes that are running the pods. There's a new concept that I've been working on, that focus on, and that's the concept of an ingress. And so with an ingress, it works with an ingress controller. And so I'm working with Nginx and developing their Nginx controller. And so what's nice about that is, A, it's a Kubernetes object, and I could go go ahead and create a YAML, an ingress YAML that says, okay, I want to use this DNS name and then this path, like a URL path that maybe servers are listening to, right? And so it's using HTTP headers. And basically the replication controller is kind of a fancy load balancer, okay, that runs inside the Kubernetes cluster on a particular machine. So like what I do in my development environment, I go ahead and tag a couple of nodes called load balancer nodes, right? And then I use a node selector when I go ahead and instantiate my Nginx ingress controller, and they get provisioned here. And then I could go ahead and even use, what is it? It's a layer 2 tool for presenting that uses VRP. Now the name escapes me. Yeah. So you can use Keeple ID as well if you want multiple Nginx replication or ingress controllers. But it works with the ingress. So when I define an ingress for my application, right, I can define this microservice application. So here's my pods or a replication controller that is made up of a bunch of different pods. I create my service, and then I create my ingress to expose that service externally. And that ingress works with the Kubernetes API on one end and this replication controller. That's essentially just a pod of one or more pods. And so what the ingress controller does is it's querying the Kubernetes API, and it's saying, hey, I've got this ingress that was defined. Is a service, is it instantiated? Oh, it is, great. Let me start receiving traffic for it. So it's a way to kind of programmatically manage like a cloud load balancer that lives inside your Kubernetes cluster. And it's dynamic in the sense that you go ahead and say, all right, let's stand up this ingress controller, one or more of them. It's going to sit there and always, query the Kubernetes API. And then as I create ingresses, right, an Apache ingress or whatever ingress I want to create, the ingress controller is aware of that because when it's querying the API, it's looking for ingresses that I specify. And then we'll dynamically become a load balancer between the client that's outside of the cluster and the services that it has, or that it's nodes don't communicate with each other at all. They're communicating with the Kubernetes API. And the schedule. Kind of the same concept or same example, just instead of a client, this is now your front end pods communicating with back end pods through a service that I call. Kind of jump through that. So Cola. First of all, Cola, since very early on, one of the things that I like about the project is its diversity. Right? So there's not really a single company that's controlling the project at all. It's actually one of the most diverse projects within OpenStack. What is it? Very simple. Containerized OpenStack services. Right. So before Cola existed, you can deploy OpenStack on bare metal or virtual machines if you want to do production with OpenStack. Pretty much had one choice, and that was on bare metal. Right? And deploying applications, OpenStack is essentially an application. Deploying applications to bare metal, you have the pros and cons. And so if we treat OpenStack like an application, why can't we containerize it and get all the benefits that you would get containerizing any other application? So the original focus was, okay, let's go ahead and take all the services and containerize them, and then we'll post the images, the Docker images, to Cola Glue sitting on Docker Hub, and then it almost becomes kind of like a content management system. So if I'm an operator saying, I'd like to deploy OpenStack containers instead of bare metal, instead of me going ahead and trying to do all this stuff myself, let me just use one of these images that have already been built. And then 6 months or so into the project, there was a deployment piece that got added, and that deployment piece was Ansible. So now you've got kind of two aspects of the project. You've got the images that were built and managed kind of based on Docker best practices or OpenStack best practices. And then you've got the deployment side of, okay, right now, how do I actually get these images to run on servers in my data center? Yeah, so go to Docker Hub and just search Cola Glue, and you'll see all the images there that you can pull. Or the other aspect that I didn't put in here, but is a is kind of a nice aspect of Cola, is a tooling around it. And one of the tools is going ahead and taking and building all the images. So if you said, well, I don't want all this Cola Glue, let me build all these images because you can go look and see all the Docker files and so forth. Let me build the images and then push them down in private streams. So some of the tooling is one of the benefits of Cola as well.
In the Cola tooling, is it possible to specify your own repos to pull for? So, like, if you have your own version of Nova, patched version of Nova that you want to pull from your own repo instead of the external repos?
I don't know offhand. I know that there's ability to build from source, so I would think that you'd be able to go ahead and point to a source repository to build.
Okay. It's probably not just the repository. You want to give it a Git tag or a Git branch name or something like that, probably.
I could check that out.
I mean, it's the benefits. Again, these are the same benefits you get from containerizing any application. Just more portability, the immutability. So when I go ahead and instantiate Glance API, I know it's exactly what it is and how I specify it in my document. And just a high-level view of the architecture. And the stuff you see here, this is really, outside. Everything in blue is outside of what Cola is, but I just want to kind of give a bigger view of what you would imagine being, right? Your infrastructure or DevOps team that has a CI/CD system in place, your registry, you have Ansible, basically your management node in your environment, and you basically spit out new images that you would go ahead and instantiate your containers from. But again, this is kind of your two pieces: is Ansible for deployment, and then the content management, right? So creating these images from kind of the vast experience of the people working on that project. So I would, if you're interested in Cola, take a look at their GitHub repo. Pretty quickly, if you have any experience with Docker or Ansible, you'll see what they're doing. Pretty quickly. But here's kind of one example. I told you kind of the layering, right? So there's a base image, and it's Ubuntu, Fedora, several distros that are supported, and then there's just the layering, right? So for every service, there's a base image. This is where I talked about, like, if I made a change to the Glance base image, I need to make sure that I rebuild Glance API off that new base image. Otherwise, and same with this as well.
So not having ever used Docker. So we just had this glibc ghost issue. That's going to be, we rebuild base, or base gets rebuilt for us, and then we just layer on top of it?
Yeah, I would assume you'd have to rebuild base and then rebuild. And again, one of the tools is, it's like rebuild all on OGO and take all the Docker files and rebuild it as well. Whatever changes you make at any layer. And this is an example of kind of a start script, right? So, like I said, every container basically needs, if it's a long lived container, needs a long range service. And what it's doing, instead of saying, okay, run Lance API, it's actually running a bash script and doing basically a lot of things. So every time that the container runs, it's bringing in like its environmental variables and basically configuring itself on the fly instead of going ahead and really making it fully immutable and saying, okay, here's a full configuration Docker file. That's kind of like finding maybe like a happy medium between giving some flexibility of injecting configuration through a shell script and then running the Lance API service. And and I think another approach that I mentioned earlier too is, instead of doing that, is maybe essentially running an system within the container. But here's some of the other examples of Docker files. Again, get base, Lance base. And you just kind of see some of the packages and files and so forth that get put into. So, just like COLA, the Magnum community is diverse and strong, and the project being a year and a half old, a lot of work that's being done in the last year and a half. So very simply, what is Magnum? I mean, it's an API wrapper of existing OpenStack services to provide containers as a service, right? So what COLA is more targeted on OpenStack operators, right? I kind of walk through the scenario of, hey, I want to build an OpenStack cloud, I want to build it on bare metal, I want to build it on containers, and get some of the advantages of all this container stuff. Whereas Magnum is more of a, from an operator standpoint, I build it, but it's to expose it to users. And so,
Container as a service.
Yeah, so containers as a service.
Containers as a service, you build an OpenStack cloud containers, or is it Nova for containers?
I guess you could say it's Nova for containers. Yeah.
Instead of VMs, you get containers.
Yeah, instead of
That's Magnum.
Right. Yeah, right.
COLA is the other part.
So I'm Joe Blow, and I want to use a cloud service. I'm Joe Blow, and it's like, man, I love these containers, and I want to deploy them to the cloud. I decide OpenStack because they've got a container service. So there's ways to get around that before Magnum, but they're basic workarounds, right? As opposed to saying, let me go ahead and give me an API endpoint that I can go ahead and just deploy containers to. And I would say, I guess containers as a service is even general, right? I think Magnum, although you can talk to the Magnum API and say, create container, right? I think Magnum is probably more focused on the container orchestration, standing up a containerized environment that you could then use the native tools, if it's the Kubernetes API, the Swarm API, to instantiate containers.
We have a business service called Heroku, and then basically has some kind of push containers to it and operates in the cloud, and then suddenly you have your own little application running.
Heroku is more of a PaaS. And so I don't know where they're at with like supporting Docker or containers. I haven't really. But I know the other PaaSes, OpenShift, who I used to be heavily involved in, they completely rewrote OpenShift probably 2 years ago and basically built. I believe Cloud Founders doing the same thing.
So is this a competing project with Nova?
not necessarily, and I was going to put a slide in here, kind of like the evolution of containers. You know, it's like there's Nova Docker, and then there was Docker supporting Heat, and and then Magnum came around and basically just kind of squashed those other projects. I mean, you probably still find Nova Docker out there, but take a look at it, no one's really nothing's happening. So Magnum kind of just took the show, and rightfully so. Like Nova Docker is like, okay, let me build a driver for containers within a compute service. Well, we're talking two different worlds, right? I mean, it's two different views. We're talking virtual machines and processes, right? So there were certain features and functionality that Nova Docker would never be able to support when you look at the matrix, the Nova matrix, and that caused a lot of problems, right? Where it was included, and then Nova Docker got kicked out. But it was just like, okay, we can't treat containers like virtual machines. They're different. And that was one of the big reasons why. There's three main components to Magnum. There's the API, the conductor, and then the client. API is a RESTful API, and it's you can stand up multiple instances. It's concurrent. I think there's only still a limitation of a single conductor. The conductor is kind of a translator between the API and talking to the database, or basically talking or realizing API constructs into like heat templates. So what's happening really behind the curtains is heat templates. So think of, I said that Magnum's kind of like an API wrapper to OpenStack, probably more of an API wrapper to Heat, because it is relying, everything behind the scenes is heat templates. And one of the projects that one of our guys is working on is actually simplifying those templates because they've gotten out of control. Right? So there's main templates for the three different container orchestration engines that are supported by Magnum, and those are Swarm, Kubernetes, and Mesos. And then within those three categories, there's templates for the different OS distros, and all of a sudden it's like, oh my gosh, we've got like 60 different templates when there's like 80% overlap. So over the last, basically since Tokyo, working with the Heat community, and finally got support within Hot for conditionals. And so now we'll be able to have a reduced number of templates, and then just actually have conditionals within those templates. So if I ask Magnum to say, okay, realize a Kubernetes COE with a Fedora distro, those just become conditional logic within a single Heat template. Yeah, so let's see here. So each COE has its own default network. Kubernetes uses Flannel, and then Docker and or Swarm and Mesos use traditional Docker networking. Right?
It's all behind the Magnum API to use Neutron for this.
So the only thing that Neutron is doing is when you create a Bay model, you're going to go ahead and say so a Bay. Let's just talk about a Bay model and a Bay. So a Bay model, think of that as like a template for your bays, right? So a Bay is a collection, basically like a containerized clustering environment. So whenever you hear Bay, just think of it as that's an instantiation of a containerized clustering environment, either Swarm, Kubernetes, or Mesos, right? And the number of nodes. And so what you're basically doing is you're saying, hey, stand up a Bay. And the Bay, you actually point to a Bay model to give it all of its definitions, right? Here's the Neutron network I want you to connect to. Here's the COE I want you to use, Kubernetes or Swarm or what have you. And we can actually, I can show you some of the details in my system. But to your question is, from a Neutron standpoint, until Courier gets integrated through this networking pluggable system that I was talking about at the beginning of this talk. Until Courier comes in, we basically use the default drivers or whatever driver that you want as part of your bay. So again, going back to the bay model, the template that defines how you want to instantiate bays. One of the things you could say, hey, I want this network driver, right? And it could be Calico, Weave, or whatever. Now that's a theoretical, right? We haven't added those drivers yet. They're still just the native drivers, and those native drivers, again, Flannel for Kubernetes and Docker for Swarm and Mesos. But when I go ahead and say, create a bay, give me 10 nodes in this bay, right? So now I have a container cluster environment consisting of 10 nodes. Right now, those are 10 Nova virtual machines, right? And as part of that process, I say, connect these virtual machines to this Neutron network, right? Now, when I realize containers within that bay, they're completely oblivious to what's going on at the Neutron layer, because basically what we're doing is, if we're doing VXLAN or UDP encapsulation with Flannel, as soon as that packet wants to go off and it says, oh, look at my routing table, I need to go over this VXLAN tunnel, let me encapsulate it with this UDP port, give it my IP address, and my routing table said it's, you know, node 2 or node 3's IP address that I put on the desk. It gets encapsulated. On the other side, it breaks it open and says, oh, you want to go to this container. From a Neutron networking standpoint, all it did is see VXLAN or UDP, whatever it is, for Flannel packets. Okay.
So Magnum, all the containers are running on Nova nodes?
Yes, it's using Nova to realize the number of nodes that you specify. When I say node, it's basically talking to Heat saying, oh, here's the number of Nova virtual machines instantiate. Nova instantiate them, and off you go. Right? It's doing a lot of other things there as well, and I could actually walk you through the templates so you can see what's going on.
If you had Ironic, you could do it on bare.
You can. That's one of the things that we're working on. So
What?
there's some code out there
Couldn't you?
because it's not supported in Magnum. And
But it's
Ironic, I could pull up the Etherpad from Tokyo. Ironic, we can work around it. So in the one of the Magnum sessions in Tokyo, the PTL, some of the cores came in from Ironic, and we had a whole discussion on this. We need to add bare metal support to Magnum. And so we walked through the templates, and it's basically, I can't remember off the top of my head, it's how we basically create the VM. Like from Ironic standpoint, it's the way that it's implemented is the way you would do it from a command line. We'd say instantiate, Nova, Nova run or whatever it is, and give it this glance image, and then give it this Neutron network ID, right?
Right.
We don't do that way, right? We actually provision a Neutron port,
And then
we say, hey, attach it to that, and that's when the Ironic, oh, we can't support. And then there's because Ironic has big support from the Rackspace team.
Right.
They said, oh, well, we have some code, but it's that. And we said, okay, well, maybe we could work on this because it's something that we wanted for a while. And they said, no, we're going to support this, right? Blah blah blah. And so one of the guys on my team, Dane, is focused on this, and I think he's actually working with one of the commits to bring it in. So we're hoping to actually have that support in Austin. Shout out in Austin.
But isn't the way that you spin up ports directly related to how Heat expects you to spin up ports when spinning up a VM under Neutron? Because it wants you to create the network, create a port on the network, and root the VM with that port. And so that workflow, so your constraint necessarily isn't Magnum, it's Heat. Okay.
And that's what I'm saying, like everything funnels through Heat. So when you think of Magnum, think of an API, like a container-focused API wrapped around Heat. It's essentially what it is. Okay. And so yeah, to your point, it's really kind of that limitation of how Heat orchestrates the network and connecting container or Nova virtual machines to a Neutron network. And again, we kind of brainstormed. We said, okay, at the surface, it seems like we could work around this, but the Ironic team said no. We want to actually, because I guess they kind of heard a similar issue from someone else as well. So, so yeah, theoretically it should work, but until this code drops in Ironic, and then we work on all the template stuff within Magnum, as well as some things in the conductor. So it's coming together. And that's one of our, I mean, so this last cycle, the focus was pluggable networking, simplifying the templates, and then Ironic support. And basically, you know, the pluggable networking is done and merged. The spec for the conditional logic within HOT, that was approved just a couple weeks ago, and there's a review out there that one of our guys, Rob Popier, is working on. So, you know, if anyone wants to afterwards, you know, ping Shannon, and I can kind of give you some of the details of those commits and so forth. Yeah, if it's something you really want to do, yeah, I mean, we'd love to get other people to kind of kick the tires or contribute, whatever. You know, I've already kind of talked about this. What is a bay and a bay model? There's other objects within the system. These are just native objects from Kubernetes, so no difference when we talk about a replication controller, a service, or pod. And I think there's some for debate on, you know, again, does Magnum continue trying to natively support these objects within the native tooling or not? So we'll see. I think that's going to be one of the topics for discussion in Austin. I know it was in Tokyo, and I think most of the community said, you know what, let's not actually have Magnum support that. You know, good examples are just Kubernetes is moving so fast. I mean, the objects that I told you about here, the service, and I talked to you about the ingress, and I could see that actually having some legs under it. You know, it's supported in 1.1 of Kubernetes, and it's like, Magnum doesn't have support for that. Magnum doesn't have support for that. Within Kubernetes, I can go ahead and just pass a YAML that has sections to it for the service, for the ingress, for the pod, and pass that to Kubi API, but I can't do that with Magnum. So it's like, kind of the writing was on the wall. It's like, you know, unless it's hard to keep track when you layer on top of an existing API when it's changing and things are moving so quickly. There's always that lag. You know, again, this is the architecture, and really, you know, it's the API, the conductor, the client. And pretty much everything funnels through OpenStack, right? So, through OpenStack Heat. And essentially this conductor is mapping entry points, Python entry points, into these Heat templates based on some type of parameter you pass to it. So when I pass a parameter such as distro equals atomic and COE equals Kubernetes, the conductor basically says, oh, that's a match to this particular Heat template. Let me go ahead and instantiate what the call requested by passing it to Heat and passing the appropriate template to Heat. How are we doing with timing?
Well, right, I think I want some more food. I'm just going to toss it or something afterwards.
Yeah, there's lots of food, and also there's some Frisbees over there we should pass out at some point. But
Do we have time for you to run through your Magnum?
Should we take a break?
Yeah.
So there's a couple of people over here lobbying for a short break.